Hello. For today's lab, we were supposed to determine the mass of a black hole by analyzing the motion of an orbiting star over the time period of 1 day, which is 86,400 seconds. We were given a file containing position data for this star over that time period, and I calculated the mass of the black hole using Newton's law of universal gravitation, which is shown here. Now, we were given the mass of the star, and we were able to calculate the radius between the motion of the star and the black hole using a Python program we had set up. And from that, we can use this second formula to solve for the mass of the black hole, which is m2. In my case, I figured and confirmed that the mass would be 5.072 times 10 to the 31 kilograms. Now, here are the physics principles that I used to determine the force of the black hole acting on the star. In our case, we're supposed to assume that the black hole is the only force that contributes to the motion of the star. Now, we know that the momentum is the mass times the velocity, and we can calculate the velocity by using the position divided by the time in the given position file. And then we can get the change in momentum over the change in time, which we assume to be the net force. And we also know that the dp over dt, the change in momentum over time, is the sum of the parallel and perpendicular components of the change in momentum over change in time. Parallel is in the direction of the motion, and perpendicular is the curving motion, so whether it rotates to the right or to the left in relation to its motion. Now, here's the code for the Python file that I used to model the motion of the star. Unlike in our previous labs, we're not inserting initial conditions to predict the motion of the star. We're using the motion to predict what forces were acting on it. Now, I've put the initial conditions here: the black hole position, the star mass, and right here I've got the way to calculate velocity. I go through and I find the position of the x and the position of the y, and I do the delta x over delta t to get the velocity, and delta y is the same thing, it's delta y over delta t. And now here's our loop that calculates the momentum. The momentum is the mass times the velocity. I've got initial and final, and then you've got the change in momentum over the change in time gets you dp over dt. And over here I've got the net force equals dp over dt. And finally, I've got the parallel and perpendicular components of the net force calculated. The parallel component was the change in the magnitude of the momentum times the unit vector for the momentum. And the perpendicular component was just, since the sum of the parallel and perpendicular components equals the dp over dt, I just did since we know the dp over dt, I subtracted the parallel component to get the perpendicular component. And now here's where I calculated the black hole mass. I've got the distance calculated using the Pythagorean theorem to just do the square root of a squared plus b squared to get the hypotenuse, which would be the radius. And I've got the black hole mass, which is just that magnitude of the F net times the distance squared, because we know, as in the formula I showed you earlier, that it's the net force times the radius squared over big G, the gravitational constant, times m1. So I've got that here times the m1 mass, and that's how I calculate the black hole mass. It's worth noting that the net force would be a bit different at every point, just because the calculation's not as precise as it could be, and it's not going to be exactly the same at every point. And the mass that I calculated was used from the net force that I got at the final point along the motion. But theoretically, I would have gotten very similar numbers if I would have used any of the points going all the way through the loop, because the same force would have been acting on the star at each position that it was, so it should have gotten the same net force, or close to the same net force all the way through, but I used the final position. And now here is the motion that I've got modeled. As you can see, I've got the parallel component of the dp over dt going opposite to the direction of the motion. It's on the same plane as the direction, just in the opposite way. I've got the perpendicular component that's making it rotate to the right from our perspective, and then I've got the sum of them, which is just the dp over dt, being the net force that is the only force really of the black hole pulling on the star. Now that I've successfully calculated the mass of the black hole, as I checked on WebAssign, I can address the what does it mean and what if questions. For what does it mean, the difference between the dp over dt, or delta p over delta t, and the F net is that they're really a cause and effect relationship of each other. The dp over dt is the effect of the F net acting on it, and the F net is the cause. So we can directly relate them to each other and use the same numbers, because the really only thing that's affecting the dp over dt is the F net. Now for the what if questions, if the black hole was removed and another one put in its place, as long as the motion stayed the same, the force would also have to be the same, because we calculate the force based on the motion. And if the force is the same, the mass has to be the same. As we can see in our formula, everything is directly related. If the force is different, the mass has to be different. But since the motion is the same, the force is the same, and the mass is also going to be the same. That's my video, and thanks for watching.